You think you understand how big the universe is, you've seen the images, you've read about billions of galaxies and trillions of stars, but here's what I need you to understand tonight. You don't really grasp it yet. None of us do, not fully. The true scale of the universe isn't just large, it's so incomprehensibly vast that when you finally glimpse even a fraction of it, it changes something fundamental about how you see reality. Tonight, we're going on a journey. We'll start right here, with you, sitting wherever you are, listening to these words, and then we'll zoom out, step by step, scale by scale, until we reach the edge of everything we can possibly observe, and somewhere along that journey, something is going to break in your mind. Not in a bad way, in the best way possible. You're going to experience a shift in perspective that only comes from truly confronting the scale of existence. Before we begin, if you enjoy these cosmic journeys, a like or subscribe would genuinely help this channel reach more people. It's a small thing, but in the vastness we're about to explore, small gestures still matter. Now, let's start with something familiar. Let's start with you. Right now you occupy a specific point in space. Maybe you're lying in bed, maybe you're sitting in a chair, maybe you're walking somewhere, headphones in, listening to this as the world moves around you. Your body extends roughly 5 to 6 feet from head to toe. Your mass is probably somewhere between 100 and 250 pounds. You're made of about 37 trillion cells, each one a universe of complexity unto itself. From your perspective, you're the center of everything. Your senses tell you this. Vision radiates out from your eyes. Sound reaches your ears from all directions. Touch confirms the boundaries of your skin. Everything you've ever experienced has happened from this one vantage point, this singular position in space and time, and for most of human history this made perfect sense. You were the center. Earth was the center. The sky was a dome overhead, the ground a flat surface extending in all directions. The sun and moon and stars rotated around you, marking time, providing light, but always subordinate to the human perspective. This wasn't ignorance, it was observation. It was the best conclusion you could draw from the data available to your senses. But then we started measuring things. We started looking closer and farther, and the center began to dissolve. Let's zoom out to your immediate surroundings, the room you're in right now. If it's a typical bedroom or living room, it might be 10 to 15 feet across, maybe 120 to 200 square feet of floor space, small by architectural standards but comfortable, enough space to live, to sleep, to exist. Zoom out further and you're looking at a building. A house might be 1,500 to 2,500 square feet. An apartment building could contain dozens of units like yours, stacked and arranged, each one a small pocket of human life, each one centered around someone who feels, just like you do, that they're at the center of things. Now zoom out to your neighborhood. Maybe it's half a mile across, a small grid of streets and buildings, parks and parking lots, a few thousand people living their lives, each one the protagonist of their own story, each one experiencing the world from a singular, irreplaceable point of view. Zoom out to your city. If you live in a major metropolitan area, you're now looking at something that spans 50, 100, maybe even 500 square miles. Millions of people, millions of individual centers of experience. The city glows at night from space, a cluster of light against the darkness, a signal of human presence. Cities are strange things when you think about them. They're dense concentrations of consciousness, billions of thoughts happening simultaneously, billions of decisions being made, billions of moments of joy and suffering and boredom all happening at once within a relatively tiny area. And already at this scale you're starting to feel it. The realization that you're not the center. You're one of millions in this city, one of billions on this planet. and we've barely started zooming out. Let's keep going. Zoom out to your country. The United States, if that's where you are, covers about 3.8 million square miles. That's enormous by human standards. You could drive for days in a single direction and still be within the same national borders. The geography varies dramatically. Mountains, plains, deserts, forests, coastlines. Hundreds of millions of people scattered across this vast landscape, each one living a complete, complex life. Zoom out further and you're looking at North America, the entire continent. 9.5 million square miles, 3 major countries, dozens of smaller ones, over 500 million people, an entire tectonic plate, a massive piece of Earth's crust floating on the mantle beneath. And now, for the first time, you can see the curvature. The horizon bends. Earth is not flat. It's a sphere, and you're standing on the surface of that sphere, held down by gravity, rotating along with it at about 1,000 miles per hour at the equator, though you don't feel the motion at all. Let's zoom out one more step and see Earth in its entirety. This is the view the Apollo astronauts had when they travelled to the moon. The whole planet floating in the void, blue and white and green and brown, alive and dynamic and singular. Earth has a diameter of about 7,626 miles at the equator. The circumference is roughly 25,000 miles. If you wanted to walk around the entire planet, assuming you could walk on water and didn't stop to rest, it would take you years. Earth's surface area is about 197 million square miles. About 71% of that is covered by oceans. The remaining 29% is land divided into 7 continents, over 190 countries, countless cities and towns and villages. About 8 billion people live on Earth right now. 8 billion individual human beings, each with their own thoughts, their own desires, their own fears and hopes and dreams. Every single person you've ever known, everyone you've ever heard of, everyone who has ever existed in all of human history, lived and died on this planet. Every empire that rose and fell, every war, every discovery, every work of art, every moment of love and every moment of hatred, all of it happened here, on this small world. From this vantage point from space, Earth looks peaceful. You can't see the borders. You can't see the conflicts. You can't hear the noise of 8 billion lives being lived simultaneously. You just see a beautiful, fragile sphere hanging in the darkness illuminated by the sun. But here's where things start to shift, because Earth, as large as it seems, is small, very small, and we're about to find out just how small. Let's introduce our first comparison. The Moon, our closest neighbour in space. The Moon orbits Earth at an average distance of about 238,850 miles. That's roughly the distance you'd travel if you drove around Earth's equator 10 times. It seems far, and it is far by any human standard. When astronauts travelled to the Moon in 1969, it took them about 3 days to get there. The Moon itself has a diameter of about 259 miles. That's about 27% of Earth's diameter. So the Moon is smaller, but not drastically so. If Earth were a basketball, the Moon would be about the size of a tennis ball. But here's the critical detail that most people miss. The distance between Earth and the Moon is enormous compared to their sizes. You could fit about 30 Earths in a line between us and the Moon. 30 complete planets side by side filling the gap. That's how much empty space exists in what we consider our immediate neighbourhood. When you see images of Earth and the Moon together, they're almost always shown much closer than reality. The actual distance is so large that it's inconvenient for illustration. This is your first real hint that space is not like the maps we draw. Space is mostly empty. Vast, overwhelming, almost oppressive amounts of nothing, punctuated by tiny islands of matter. The Earth-Moon system is unusual in our solar system. Most moons are tiny compared to their parent planets. Jupiter's largest moon, Ganymede, is bigger than our moon, but Jupiter itself is so massive that Ganymede looks like a pebble by comparison. Our moon is large relative to Earth. Some astronomers call the Earth-Moon system a double planet because of this unusual size ratio. The moon's presence has shaped Earth in profound ways. It creates the tides, pulling the oceans toward it as it orbits. It stabilizes Earth's axial tilt, preventing wild climate swings that might make complex life impossible. Without the moon, Earth might be a very different place, a less stable place, a place where life had a harder time taking hold. The moon is also slowly drifting away from us. Each year it moves about 1.5 inches farther. This happens because of tidal interactions between Earth and the moon. Billions of years ago, the moon was much closer. A day on Earth was much shorter, maybe only 5 hours long. The moon loomed huge in the sky. As time passes, it drifts farther away, and Earth's rotation slows. Eventually, billions of years from now, Earth and the moon will be tidally locked. Each will show only one face to the other, rotating in perfect synchronization. But we're not here to talk about the moon for long. We need to keep zooming out. Because the moon is just the beginning. Our next comparison takes us to the sun. The sun is the reason we exist. It's the engine that drives almost all life on Earth. Without its light and heat, our planet would be a frozen, lifeless rock. But the sun is also where Earth's size truly begins to shrink. The sun has a diameter of about 864,000 miles. That's 109 times larger than Earth's diameter. If Earth were a marble, the sun would be a sphere about 10 feet across. But diameter doesn't capture the full picture. Let's talk about volume. The sun's volume is so enormous that you could fit about 1.3 million Earths inside it. 1.3 million. Every mountain, every ocean, every continent, every city, every forest, every human being who has ever lived, all of it could fit inside the sun 1.3 million times over, and there would still be room left. And the sun isn't even a large star. It's average. Completely, utterly average. Astronomers classify it as a G-type main sequence star, a yellow dwarf. There are billions of stars just like it in our galaxy alone. The sun contains 99 to 86% of all the mass in our solar system. Everything else, all 8 planets, all the moons, all the asteroids and comets and dust, all of it combined makes up only 0.114% of the total. The sun is the solar system in terms of mass. Everything else is a rounding error. The sun sits about 93 million miles away from Earth. We call this distance 1 astronomical unit, or AU. Light from the sun takes about 8 minutes and 20 seconds to reach us. That means if the sun suddenly vanished, we wouldn't know for over 8 minutes. We'd still see it shining in the sky because the light telling us it's gone would still be travelling toward us. If you drove a car at highway speed toward the sun, it would take you about 176 years to get there. The fastest spacecraft humanity has ever built, the Parker Solar Probe, travels at speeds exceeding 400,000 miles per hour at its closest approach to the sun. Even at that incredible velocity, it takes months to make the journey. The sun produces energy through nuclear fusion. Every second it converts about 600 million tons of hydrogen into helium. This process releases an almost unimaginable amount of energy. The sun generates more power in 1 second than all of human civilization has produced throughout its entire history. The surface temperature of the sun is about 10,000 degrees Fahrenheit. The core, where fusion occurs, reaches about 27 million degrees Fahrenheit. The pressure at the core is about 260 billion times Earth's atmospheric pressure. These are not conditions where matter behaves in familiar ways. At the sun's core, the rules change. Atoms are stripped of their electrons. Nuclei slam into each other with such force that they fuse, releasing energy in the process. This is the same process that powers hydrogen bombs, but on a scale so vast that human weapons seem like firecrackers by comparison. The sun has been burning for about 4.6 billion years. It's roughly middle-aged. It has enough hydrogen fuel to keep fusing for another 5 billion years or so. After that, it'll begin to die. It will swell into a red giant, consuming Mercury, Venus, and possibly Earth. Then it will shed its outer layers and collapse into a white dwarf, a dense, slowly cooling ember about the size of Earth, but with much of the sun's original mass compressed into that small volume. But that's billions of years away. For now, the sun is stable, reliable. It rises and sets with perfect regularity, a cosmic clock that has governed life on Earth for as long as life has existed. Looking at the sun from our perspective on Earth, it's easy to forget how small we are. The sun appears as a bright disk in the sky, about the same size as the moon. This is a complete coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This coincidence gives us total solar eclipses, moments when the moon passes directly between Earth and the sun and blocks it out perfectly, revealing the sun's corona, its outer atmosphere. But let's keep zooming out, because the sun, as massive as it is just one star, and we need to see what else is out there. Let's expand our view to include the solar system. The 8 planets orbit the sun at various distances. Mercury is closest, about 36 million miles from the sun. Neptune, the farthest, orbits at about 2.8 billion miles. That's 30 AU. The solar system is much larger than most people realise. If you include the Kuiper belt, a region of icy bodies beyond Neptune where Pluto resides, the solar system extends to about 50 AU. And if you include the Oort cloud, a theoretical shell of comets surrounding the solar system, it might extend as far as 100,000 AU. That's nearly 2 light years. A light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 year, it covers about 5.88 trillion miles. The Oort cloud, if it exists as theorized, extends nearly 2 light years from the sun. That means the solar system, at its farthest edge, is almost halfway to the nearest star. And this brings us to the next scale, the stars. Our nearest stellar neighbour is Proxima Centauri, part of the Alpha Centauri star system. It's about 4.24 light-years away. That's roughly 25 trillion miles. If you could drive a car at highway speed toward Proxima Centauri, it would take you about 50 million years to get there. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. It's currently about 14 billion miles from Earth, travelling at about 38,000 miles per hour. At that speed, it would take Voyager 1 about 75,000 years to reach Proxima Centauri. Except it's not headed in that direction, so it never will. The distances between stars are so vast that they defy human intuition. We've never travelled to another star. We've never even come close. The farthest we've sent humans is the moon, less than 250,000 miles away. The farthest we've sent machines is barely out of our solar system's immediate neighbourhood. And here's the thing, space is mostly empty at this scale too. Stars are tiny islands of matter separated by oceans of void. If you shrunk the Milky Way galaxy down to the size of the United States, each star would be about the size of a grain of sand, and those grains of sand would be separated by distances of hundreds of feet. That's how sparse star systems are. Even in our densest star clusters, collisions between stars are extraordinarily rare. There's just too much empty space. And here's the thing, space is mostly empty at this scale too. Stars are tiny islands of matter separated by oceans of void. If you shrunk the Milky Way galaxy down to the size of the United States, each star would be about the size of a grain of sand. And those grains of sand would be separated by distances of hundreds of feet. That's how sparse star systems are. Even in our densest star clusters, collisions between stars are extraordinarily rare. There's just too much empty space. Let's talk about what stars actually are, because understanding them helps us grasp the scale we're dealing with. Stars are massive spheres of plasma held together by their own gravity, generating energy through nuclear fusion in their cores. They come in different sizes, different colours, different temperatures. Our Sun is a medium-sized yellow star, but there are stars much, much larger. Take Betelgeuse, a red supergiant in the constellation Orion. Betelgeuse has a diameter about 700 times larger than the Sun. If you placed Betelgeuse where our Sun is, its surface would extend past the orbit of Mars. Earth would be inside the star, vaporized instantly, and Betelgeuse isn't even the largest star we know of. UY Scuti, a red hypergiant, has a diameter roughly 1,700 times larger than the Sun. If UY Scuti replaced our Sun, its surface would reach beyond the orbit of Jupiter. Saturn would be inside it. These stars are so large that their scale breaks our ability to visualize them. You can say the numbers, you can write them down, but truly comprehending what it means for something to be 700 times larger than an object that's already 109 times larger than Earth, that's where human intuition fails. But size isn't everything with stars. Mass matters too, and some stars pack incredible mass into relatively small volumes. Neutron stars are the collapsed cores of massive stars that exploded as supernovas. A neutron star might have a diameter of only about 12 miles, roughly the size of a city, but that tiny sphere contains more mass than our entire Sun. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity on the surface of a neutron star is so intense that if you dropped an object from a height of just 1 meter, it would hit the surface at about 2 million meters per second. That's almost 1% of the speed of light. The escape velocity from a neutron star is about 100,000 kilometers per second, roughly 1/3 the speed of light. These objects bend space and time around them so severely that light itself is affected. If you could somehow stand on the surface of a neutron star and look at the horizon, you'd see behind yourself because the star's gravity would bend light from behind you around the curve of the star and into your eyes. But you couldn't stand on a neutron star. You'd be instantly crushed into a layer of atoms 1 atom thick on its surface, added to the thin atmosphere of iron vapor that surrounds these objects. And then there are black holes. Black holes are what happens when massive stars dozens of times more massive than our Sun, reach the end of their lives and collapse. The core implodes, and gravity becomes so strong that nothing, not even light, can escape. A black hole's defining feature is its event horizon, the boundary beyond which escape becomes impossible. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers in radius. That's tiny. A sphere 6 kilometers across containing the mass of an object 1.4 million kilometers in diameter. The density is beyond comprehension. At the center of a black hole, according to our current understanding of physics, is a singularity. A point of infinite density where all the mass is concentrated. But this is where our physics breaks down. General relativity and quantum mechanics give different answers about what happens at a singularity, and we don't yet have a theory that reconciles them. What we do know is that black holes exist. We've observed them indirectly through their effects on nearby matter. We've detected gravitational waves from colliding black holes. And in 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's event horizon, a supermassive black hole at the centre of the galaxy M87. Speaking of supermassive black holes, let's zoom out again and talk about the structure of galaxies. Because stars don't float randomly through space, they're organised into galaxies, enormous rotating systems of stars, gas, dust, and dark matter, all bound together by gravity. Our galaxy is called the Milky Way. From Earth, on a clear night far from city lights, you can see it as a hazy band of a light stretching across the sky. That band is your view of the galaxy from inside it. We're looking through the disk, seeing the combined light of billions of stars too distant and too numerous to resolve individually. The Milky Way is a barred spiral galaxy. It has a central bulge, a bar-shaped structure through the middle, and spiral arms extending outward. The disk of the Milky Way is about 100,000 light-years in diameter. That's 100,000 times the distance light travels in a year. It's roughly 587,000 trillion miles across. The Milky Way contains between 100 billion and 400 billion stars. Let's use a conservative estimate and say 200 billion. That's 200 billion suns, each potentially with its own system of planets, each a possible home for life. Our Sun is located about 26,000 light-years from the galactic centre, roughly halfway out along one of the spiral arms. We're not in a special location. We're in a fairly average spot in a fairly average galaxy. The solar system orbits the galactic centre at about 514,000 miles per hour. At this speed, it takes about 230 million years to complete one orbit. The last time Earth was in this position in the galaxy, dinosaurs were just beginning to emerge. Since then, we've travelled once around the entire galaxy and are now passing through the same region of space again. At the centre of the Milky Way is a supermassive black hole called Sagittarius A star. It has a mass of about 4 million times that of our Sun. That's 4 million suns worth of mass compressed into a region smaller than the orbit of Mercury. Sagittarius A star is relatively quiet for a supermassive black hole. It doesn't consume much matter, but occasionally a star or a cloud of gas strays too close, and the black hole tears it apart, feeding on the debris and emitting powerful radiation in the process. Almost every large galaxy has a supermassive black hole at its centre. These aren't stellar black holes, the remnants of dead stars. These are monsters, millions or even billions of times more massive than the Sun. We don't fully understand how they form. Some might have formed from the collapse of massive gas clouds in the early universe. Others might have grown by consuming stars and merging with other black holes over billions of years. The supermassive black hole at the centre of M87, the one we have an image of, has a mass of about 6.5 billion times that of the Sun. Its event horizon is about 20 billion kilometres across. That's larger than the orbit of Neptune, and that's just the point of no return. The black hole's influence extends much farther, shaping the motion of stars and gas throughout the galaxy. The Milky Way doesn't exist in isolation. It's part of a small group of galaxies called the Local Group. The Local Group contains about 80 galaxies, but most of them are small dwarf galaxies. There are 3 large galaxies in the Local Group: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda is the largest of the 3. It's about 2.5 million light-years away from us. That's 2.5 million times the distance light travels in a year. It's roughly 15 quintillion miles. At the speed Voyager 1 is travelling, it would take about 650 million years to reach Andromeda. Andromeda is visible to the naked eye from Earth on a clear, dark night. It appears as a faint, fuzzy patch of light. But that faint patch contains about 1 trillion stars. 1 trillion individual suns, each potentially with planets, each a complete solar system. When you look at Andromeda, you're seeing light that left those stars 2.5 million years ago. When that light began its journey, humans didn't exist yet. Our ancestors were still early hominids, just beginning to use simple stone tools, and that light has been travelling through empty space ever since, covering 5.88 trillion miles every year, until finally, tonight, it reaches your eyes. Andromeda and the Milky Way are on a collision course. They're moving toward each other at about 250,000 miles per hour. In about 4.5 billion years, they'll collide. But galactic collisions aren't like car crashes. Galaxies are mostly empty space. The stars are so far apart that very few, if any, will actually collide. Instead, the two galaxies will pass through each other, their gravity disrupting each other's structures, pulling stars out of their orbits, triggering bursts of new star formation as gas clouds collide and compress. Over hundreds of millions of years, the two galaxies will merge into a single, larger elliptical galaxy. By that time, if Earth still exists, if humanity or its descendants are still around, the night sky will look completely different. Andromeda will dominate the sky, growing larger and larger as the collision progresses. Eventually, there won't be two separate galaxies anymore. There will just be one, a new structure born from the merger, with a new supermassive black hole at its centre, formed from the combination of the Milky Way's black hole and Andromeda's. But let's keep zooming out, because the local group is just a small cluster in a much larger structure. The local group is part of the Virgo supercluster, a massive collection of galaxies bound together by gravity. The Virgo supercluster contains at least 100 galaxy groups and clusters, including the Virgo cluster, which contains about 1/300 galaxies. The Virgo supercluster spans about 110 million light-years. That's 110 million times the distance light travels in a year. It contains roughly 100 trillion stars. But even the Virgo supercluster isn't the end. Recent observations have revealed that the Virgo supercluster is part of an even larger structure called the Laniakea supercluster. Laniakea means immeasurable heaven in Hawaiian. It's an appropriate name. Laniakea contains about 100,000 galaxies. It spans about 520 million light-years. The mass of Laniakea is approximately 100 million billion times the mass of our Sun. That number is so large it loses meaning. You can write it down, you can say it out loud, but your brain cannot truly hold it. We've evolved to understand numbers that matter for survival. Tens, hundreds, maybe thousands. Numbers that correspond to quantities we might encounter in daily life. But 100 million billion? That's not a number we can visualize. It's just a symbol, a placeholder for a magnitude we can't really grasp. And we're still not done zooming out. Laniakea is just one supercluster among many. The observable universe contains about 10 million superclusters, and between those superclusters are voids, vast regions of space where very few galaxies exist. These voids are enormous. The Buta's void, one of the largest known, spans about 330 million light-years. It contains only about 60 galaxies, far fewer than you would expect in such a large volume. If the Milky Way were in the centre of the Buta's void, we wouldn't have known that other galaxies existed until the 1960s. The nearest large galaxy would have been too far away to see with earlier telescopes. The universe has structure at these scales. Galaxies cluster together in groups and clusters. Clusters gather into superclusters, and superclusters form the boundaries of voids, creating a cosmic web, a vast foam-like structure where galaxies trace out filaments and sheets surrounding empty regions. This structure formed over billions of years, driven by gravity and the initial density fluctuations in the early universe. Shortly after the Big Bang, the universe was almost perfectly smooth, but not quite. There were tiny variations in density, regions that were slightly more dense than others. Over time, gravity amplified those differences. Denser regions attracted more matter. Less dense regions lost matter. Over hundreds of millions of years, over billions of years, this process created the structure we see today. Now let's zoom out one final time and look at the observable universe as a whole. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old, so you might think the observable universe is 13.8 billion light-years in radius, but it's not. The universe has been expanding during the time that light has been travelling. Space itself stretches, carrying distant galaxies away from us. By the time light from a distant galaxy reaches us, that galaxy has moved much farther away. The observable universe has a radius of about 46.5 billion light-years. That's the co-moving distance to the edge of what we can observe. The diameter is about 93 billion light-years. The observable universe contains at least 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The total number of stars in the observable universe is estimated to be around 1 septillion. That's 1 followed by 24 zeros. 1,000 stars. And each of those stars is a sun. Many of them have planets. Some of those planets are in the habitable zone, the region where liquid water can exist. Some of those planets might have life. We don't know. We've only found life on one planet so far, Earth. But the numbers suggest that if life can arise if the conditions are right, then the universe should be teeming with it. The sheer number of possible locations is staggering. But here's the critical thing to understand. The observable universe is just what we can see. It's limited by the speed of light and the age of the universe. There's no reason to think the universe stops at the edge of what we can observe. In fact, most cosmologists believe the universe extends far beyond our observable horizon. How far? We don't know. It might be infinite. It might be finite, but much, much larger than the observable portion. We might never know for certain because we can't observe beyond the light cone, the region from which light has had time to reach us. And every second that boundary expands. Light from more distant regions reaches us. But the universe is also expanding. Distant galaxies are moving away from us, and the farthest ones are moving away faster than the speed of light. Not because they're travelling through space faster than light, but because space itself is expanding between us and them. This means there are galaxies we will never be able to see. Galaxies that exist right now but are so far away that light from them will never reach us because the space between us is expanding faster than light can cross it. These galaxies are beyond our cosmic horizon, forever inaccessible, forever invisible. Let's bring this back to Earth for a moment. Because we've travelled so far, zoomed out so many times, that Earth has disappeared. It's invisible at this scale. If you made a scale model of the observable universe, Earth would be far smaller than an atom. It would be smaller than a quark. It would be so incomprehensibly tiny that there's no instrument sensitive enough to detect it. The observable universe has a volume of about 4 times 10 to the 80th power cubic meters. That's 4 followed by 80 zeros. Earth has a volume of about 1 trillion cubic kilometers. In the scale of the observable universe, Earth's volume is less than 10 to the negative 60th. That's a decimal point followed by 59 zeros and then a 1. It's effectively 0. Earth is so small compared to the observable universe that it might as well not exist. And yet, Earth is everything to us. Every human who has ever lived was born on Earth. Every thought you've ever had occurred in a brain that was standing, sitting, or lying on the surface of Earth. Every emotion, every memory, every moment of your life happened here, on this impossibly tiny speck. Carl Sagan famously reflected on this after seeing an image of Earth taken by Voyager 1 from the edge of the solar system. In that image, Earth appeared as a pale blue dot, a single pixel of light against the vastness of space. Sagan wrote about how every king and peasant, every saint and sinner, every civilization that rose and fell, all of it happened on that pale blue dot. He talked about how the Earth is the only home we've ever known, and how it highlights the absurdity of human conflicts and divisions when you see them from this perspective. And Sagan was right. When you truly confront the scale of the universe, human concerns start to look different. Not meaningless, exactly, but different. The borders we draw on maps, the conflicts we fight over resources, the arguments about who owns which piece of land, all of it happens on a world so small that from just a modest distance, you can't even see it anymore. This perspective doesn't solve human problems. It doesn't make suffering less real or injustice less important. But it does provide context. It reminds us that we're all on the same, impossibly small world, floating through an incomprehensibly vast cosmos, and that maybe, just maybe, we should spend less time fighting each other and more time appreciating the extraordinary fact that we exist at all. But let's dig deeper into what this scale means, because it's not just about size, it's about time, distance, and the fundamental limits of what we can know and experience. Light is the fastest thing in the universe. Nothing can travel faster than light in a vacuum. The speed of light is 186,282 miles per second. In 1 year, light travels about 5.88 trillion miles. That's 1 light year. When we look at a star that's 100 light years away, we're seeing light that left that star 100 years ago. We're not seeing the star as it is now. We're seeing it as it was a century ago. When we look at the Andromeda Galaxy, 2.5 million light years away, we're seeing it as it was 2.5 million years ago. The galaxy might look completely different now. Stars have been born and died in the time it took that light to reach us. But we won't know what Andromeda looks like today for another 2.5 million years. This creates a strange situation. The farther out we look, the farther back in time we see. When we observe the most distant galaxies, the ones at the edge of the observable universe, we're seeing them as they were more than 13 billion years ago, less than 1 billion years after the Big Bang. These galaxies were young then, small, irregular, full of hot, bright stars. They've had 13 billion years to evolve since the light we're seeing left them. They might be massive elliptical galaxies now, or they might have merged with other galaxies and ceased to exist as distinct entities. We don't know. We can't know. The information about their current state won't reach us for billions of years. This also means that if there are intelligent beings on a planet orbiting a star in one of those distant galaxies, and if they have telescopes powerful enough to see Earth, they're not seeing Earth as it is today. They're seeing Earth as it was billions of years ago, long before humans existed, long before complex life existed. They might be looking at Earth right now and seeing a world covered in simple microbes, with no hint of the civilization that would eventually develop here. And if they're trying to communicate with us, if they sent a signal in our direction, that signal has been travelling through space for billions of years. It might reach us tomorrow. It might reach us in 1 million years. Or it might never reach us because the expansion of space has carried us beyond the distance their signal can travel. The universe is not just big, it's old, and the combination of size and age creates distances that are fundamentally unbridgeable with our current technology. The nearest star system, Alpha Centauri, is 4.24 light-years away. With current propulsion systems, it would take tens of thousands of years to reach it. We could, in theory, send a probe. It would be a one-way trip. The probe would travel for millennia, far longer than human civilization has existed, and by the time it arrived, everyone who built it, everyone who sent it, everyone who even remembered it existed, would be long dead. And that's just the nearest star. Most stars are much, much farther away. The centre of our galaxy is 26,000 light years away. At the speed of our fastest spacecraft, it would take about 450 million years to get there. The Andromeda Galaxy, forget it. Even travelling at the speed of light, which is physically impossible for any object with mass, it would take 2.5 million years to reach Andromeda. And by the time you arrived, Andromeda would have moved. The universe would have continued expanding while you were in transit. This is the tyranny of distance. The universe is so large and the speed of light is so finite that most of the universe is effectively unreachable. We can observe it, we can study it, we can learn about it. But we can never go there. Not with technology we currently have or can even imagine developing in the foreseeable future. Some scientists speculate about ways around this. Wormholes, hypothetical tunnels through space-time that might connect distant regions of the universe. Warp drives, theoretical propulsion systems that might compress space in front of a spacecraft and expand it behind, allowing faster-than-light effective travel without actually moving faster than light locally. Generational ships, massive vessels that could travel for thousands of years, carrying multiple generations of humans who would live and die aboard the ship while it slowly crossed interstellar distances. But these are all speculative. Wormholes might not exist, and even if they do, we have no idea how to create or stabilize one. Warp drives require exotic matter with negative energy density, which we've never observed and might not exist. Generational ships face enormous technical, social and psychological challenges. How do you maintain a functioning society aboard a spacecraft for thousands of years? How do you prevent the mission from being abandoned by descendants who never chose to be part of it? These are solvable problems perhaps, but we're nowhere close to solving them. And even if we did solve them, even if we developed the technology to travel to other star systems, we'd still be confined to a tiny bubble of space. The Milky Way is 100,000 light years across. Even travelling at the speed of light, which again is impossible, it would take 100,000 years to cross the galaxy, and the Milky Way is just one galaxy among trillions. The observable universe is so large that the light from its farthest regions has been travelling for over 13 billion years and has still only crossed a fraction of the total distance. This is humbling, deeply, profoundly humbling. We're confined to a tiny region of space by the laws of physics. We can see the universe, we can study it, we can understand it, at least partially. But we can never experience most of it firsthand. We are like people living in a small village who can see distant mountains on the horizon but can never visit them. Except the scale is so much larger that the analogy barely holds. The village is Earth, the mountains are galaxies, and the distance between them is so vast that it makes the word distance seem inadequate. Let's talk about what fills all this space. Because when we say space is mostly empty, that's true, but it's not the complete picture. The vacuum of space isn't a perfect vacuum. It's filled with extremely low-density gas, mostly hydrogen and helium. In the space between stars, you might find 1 atom per cubic centimetre. That's incredibly sparse. On Earth, at sea level, there are about 10 to the 19th power molecules per cubic centimetre. The air you're breathing right now is dense beyond comprehension compared to interstellar space. In the space between galaxies, the density is even lower. You might find 1 atom per cubic metre. That's so sparse that it's almost a perfect vacuum by any practical standard. But those atoms add up. When you have volumes measured in cubic light years, even 1 atom per cubic metre represents a lot of mass. And that mass interacts. Gravity pulls on it. It clumps together over time. It forms clouds. Those clouds collapse and form stars. Those stars live and die, creating heavier elements in their cores and scattering those elements into space when they explode. New clouds form from that enriched material. New stars are born. And the cycle continues. There's also dark matter. We don't know what dark matter is. We can't see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. But we know it's there because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. The outer regions of galaxies are moving so fast that they should fly apart, but they don't. Something is holding them together. That something is dark matter. Clusters of galaxies also show evidence of dark matter. The galaxies within a cluster are moving too fast. They should escape the cluster's gravity and disperse, but they don't. Dark matter, whatever it is, provides the additional gravity needed to keep them bound. We estimate that dark matter makes up about 85% of all the matter in the universe. Only 15% is ordinary matter, the stuff that makes up stars, planets, and us. Everything we can see, everything we've ever touched, everything we've ever detected with any instrument is a small minority of the total matter that exists. The rest is invisible, undetectable except through gravity. There are many theories about what dark matter might be. Weakly interacting massive particles or WIMPs, axions, primordial black holes, modified theories of gravity that eliminate the need for dark matter entirely. But we don't know. Despite decades of experiments, we haven't directly detected dark matter particles. We've only inferred their existence from their gravitational effects. This is one of the biggest mysteries in modern physics. Then there's dark energy. Dark energy is even more mysterious than dark matter. We discovered dark energy in the late 1990s when astronomers were measuring the expansion rate of the universe. They expected to find that the expansion was slowing down due to gravity. All the matter in the universe, both ordinary and dark, should be pulling everything together, decelerating the expansion left over from the Big Bang. But that's not what they found. They found that the expansion is accelerating. Distant galaxies are moving away from us faster and faster over time. Something is pushing the universe apart. We call that something dark energy, but the name is just a placeholder. We don't know what it is. Dark energy makes up about 68% of the total energy content of the universe. Dark matter is about 27%. Ordinary matter, everything we can see and touch, is only about 5%. We live in a universe where 95% of the content is completely unknown to us. We can detect its effects, but we don't understand what it is or why it exists. This should be shocking. Imagine if you looked around your house and discovered that 95% of the objects in it were invisible, and you had no idea what they were or what they did. That's essentially the situation we're in with the universe. We've mapped its large-scale structure. We've measured its expansion. We've figured out the laws of physics that govern how it behaves. But the fundamental components, the things that make up most of its mass and energy, remain a mystery. Let's shift perspective for a moment and talk about what all this means for the possibility of life elsewhere in the universe. Earth is the only place we know for certain that life exists. But the numbers suggest that life should be common. There are at least 2 trillion galaxies in the observable universe. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. Some of those planets are in the habitable zone where liquid water can exist on the surface. Liquid water is essential for life as we know it. It's a solvent. It allows complex chemistry to occur. Without liquid water, the kind of chemistry that led to life on Earth couldn't happen, or at least it would be far less likely. NASA's Kepler mission, which operated from 2009 to 2018, discovered thousands of exoplanets, planets orbiting other stars. Many of these planets are in the habitable zone of their stars. Some are rocky, like Earth. Some are larger, so-called super-Earths. Some orbit red dwarf stars, the most common type of star in the galaxy. Red dwarfs are cooler and dimmer than the Sun, but they live far longer, trillions of years compared to the Sun's 10 billion year lifespan. If life can develop on planets orbiting red dwarfs, then those civilizations might have trillions of years to evolve and develop, far longer than Earth has existed. Based on Kepler's data, astronomers estimate that there might be billions of Earth-like planets in the Milky Way alone. Billions. And that's just one galaxy. If you multiply that by 2 trillion galaxies, the number of potentially habitable planets in the observable universe is staggering. It's almost incomprehensible. So where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" If life is common, if intelligent civilizations arise on even a tiny fraction of habitable planets, then the galaxy should be teeming with intelligent life. Some of those civilizations should be far older than ours. They've had millions or billions of years to develop technology, to spread across their star systems, to send signals or probes into space. We should see evidence of them, but we don't. We've been listening for signals from extraterrestrial civilizations for decades through programs like SETI, the search for extraterrestrial intelligence. We've heard nothing. No signals, no patterns that can't be explained by natural phenomena. The galaxy appears silent. There are many possible explanations for the Fermi paradox. Maybe life is rare. Maybe the conditions needed for life to arise are more stringent than we think. Maybe Earth is unusual in ways we don't fully appreciate. Maybe intelligent life is even rarer. Perhaps life commonly arises, but intelligence is a fluke, an evolutionary accident that happened here but might not happen often elsewhere. Maybe civilizations destroy themselves before they develop the technology to communicate across interstellar distances. Nuclear war, environmental collapse, artificial intelligence gone wrong, engineered pandemics. There are many ways a civilization could end itself, and maybe most civilizations follow that path. Maybe the distances are just too vast. Even if there are thousands of civilizations in the galaxy right now, they might be so far apart that communication is impractical. A signal from the nearest civilization might take thousands of years to reach us. And if we replied, our response would take thousands of years to reach them. By the time they received it, their civilization might have ended. Or maybe we're early. Maybe we're among the first intelligent civilizations to arise in this galaxy. The universe is 13.8 billion years old, but the conditions for life might not have been favourable until relatively recently. The first generations of stars contained almost no elements heavier than hydrogen and helium. Carbon, oxygen, nitrogen, all the elements essential for life as we know it, had to be created in the cores of stars and scattered into space by supernovas. It took billions of years for the galaxy to be enriched with enough heavy elements to allow rocky planets to form and life to develop. Earth formed about 4.5 billion years ago. Life arose relatively quickly, within the first billion years, but complex multicellular life took much longer. For most of Earth's history, life consisted of single-celled organisms. Animals didn't appear until about 600 million years ago. Humans have only existed for a few 100,000 years. Civilization is only about 10,000 years old. Industrial technology is only about 200 years old. We're newcomers on a cosmic timescale. Maybe most civilizations are still in their equivalent of the single-celled stage. Maybe we're among the first to reach this point, and in a billion years, the galaxy will be full of intelligent life, but right now it's mostly empty. Or maybe they're out there, but they're not interested in communicating. Maybe advanced civilizations have better things to do than send signals to primitive species like us. Maybe they're focused on projects we can't even imagine, manipulating space-time, building megastructures, uploading their consciousnesses into computers, and living in virtual reality is far more interesting than the physical universe. We don't know. The Fermi paradox remains one of the most intriguing questions in science, and it highlights something important about our place in the universe. We are, as far as we know, alone. Not necessarily alone in the entire universe, but alone in our observable corner of it. We've looked, we've listened, we've found nothing. Maybe we're not looking in the right way, maybe we're not listening for the right signals. Maybe evidence of extraterrestrial intelligence is all around us, but we don't recognize it because we don't know what to look for. But for now, Earth is the only place we know of where the universe has become aware of itself. That's profound. It means that if we fail, if we destroy ourselves, or allow our civilization to collapse, we might be silencing the only voice the universe has in this region of space. There might be others, far away, too distant to ever contact. But here, in our local bubble of the cosmos, we might be it. That's both terrifying and awe-inspiring. Let's talk about time again, because time is as important as space when we're discussing scale. The universe is 13.8 billion years old. That's a long time by human standards. The entirety of recorded human history is only about 5,000 years. Anatomically, modern humans have existed for about 300,000 years. Our species, Homo sapiens, is less than 0.003% as old as the universe. We're so young on a cosmic timescale that we barely register. But 13.8 billion years is actually young for the universe. The universe will continue to exist for trillions of years. Stars will keep forming for trillions of years. Eventually the universe will run out of gas. The raw material for making new stars will be depleted. Existing stars will die, and no new ones will replace them. This will happen gradually over an almost incomprehensible timescale. In about 100 trillion years, the last star will die. The universe will enter what's called the degenerate era, a time when the only objects are remnants: white dwarfs, neutron stars, black holes. These objects will slowly cool, radiating away their heat into the expanding void. After about 10 to the 40th years, even these remnants will begin to decay. Protons, the building blocks of atoms, might not be stable forever. If they decay, and some theories suggest they do, then eventually all matter will break down into radiation and elementary particles. Black holes will be the last objects to persist. But even black holes evaporate, slowly leaking energy through a process called Hawking radiation. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate. Supermassive black holes, the kind at the centres of galaxies, would take even longer, perhaps 10 to the 100th years or more. After that, the universe enters the black hole era, and then finally the dark era. A time when the universe is cold, dark, and empty. No stars, no planets, no structures, just isolated particles drifting through an ever-expanding void, getting farther and farther apart, until eventually the universe reaches a state of maximum entropy. Nothing happens anymore because there's no energy available to make anything happen. This is called heat death, the ultimate fate of the universe according to our current understanding. It's not a violent end, it's a slow fade into darkness and silence, but it's trillions upon trillions of years away. On that timescale, the age of stars, the age we're living in right now, is just the blink of an eye. We exist during a brief, bright moment in cosmic history when the universe is full of structure and complexity, when stars shine and planets orbit and life is possible. Someday, far in the future, this era will be remembered, if there's anyone left to remember it, as the golden age of the cosmos, the time when the universe was young and vibrant and full of possibility. But let's bring this back to the present, back to Earth, back to you. You've been listening to this for a while now, and you've travelled an enormous distance conceptually. We started with you, a human being occupying a few cubic feet of space, and we zoomed out until Earth disappeared, until the solar system disappeared, until the Milky Way became a speck, until even galaxy clusters became tiny in comparison to the observable universe. And somewhere along that journey, something shifted. You felt it. That sense of vertigo, that feeling of being utterly insignificant, a tiny fragment of awareness in an incomprehensibly vast cosmos. That feeling has a name. It's called the overview effect. Astronauts who travel to space often report experiencing it. When they look back at Earth from orbit, when they see the whole planet floating in the void, they experience a profound shift in perspective. Borders disappear, conflicts seem petty. The fragility of Earth's biosphere becomes apparent. The thin blue line of the atmosphere looks so delicate, so vulnerable, and they realize that everything they've ever known, everyone they've ever loved, exists on that small, fragile world. The overview effect changes people. Astronauts come back from space with a different understanding of humanity's place in the cosmos. They become advocates for environmental protection, for international cooperation, for the peaceful use of space. They've seen something that most of us will never see. They've looked at Earth from the outside, and it changed them. You don't need to go to space to experience something similar. You can experience a version of it right here, right now, by confronting the scale of the universe intellectually, by truly understanding as much as a human mind can understand just how small Earth is and how vast everything else is. This understanding doesn't diminish you. It doesn't make your life meaningless. If anything, it does the opposite. It highlights how extraordinary it is that you exist at all. Think about what had to happen for you to be here. Listening to these words, the universe had to begin. 13.8 billion years ago, all of space and time erupted from an infinitely dense point. We call this the Big Bang, though it wasn't an explosion in space. It was an explosion of space itself. Space and time came into existence simultaneously, expanding and cooling, creating the conditions for matter to form. In the first fraction of a second, the universe was unimaginably hot and dense. It was a soup of fundamental particles, quarks and gluons, too energetic to combine into atoms. As the universe expanded and cooled, those particles combined to form protons and neutrons. About 3 minutes after the Big Bang, the universe was cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements. Hydrogen, helium, a tiny bit of lithium. That was it. No carbon, no oxygen, no nitrogen. None of the elements that make up your body existed yet. The universe continued to expand and cool. For about 380,000 years, it was opaque. Photons of light couldn't travel freely because they kept scattering off the dense plasma of electrons and nuclei. But then the universe cooled enough for electrons to combine with nuclei and form stable atoms. Suddenly, light could travel freely. The universe became transparent. That light is still travelling through space today. We call it the cosmic microwave, background radiation, and we can detect it with sensitive instruments. It's the afterglow of the Big Bang, stretched and cooled by 13.8 billion years of cosmic expansion, now detectable as faint microwave radiation coming from every direction in the sky. After the universe became transparent, it entered what astronomers call the Dark Ages. There were no stars yet, just clouds of hydrogen and helium drifting through space. But those clouds weren't perfectly uniform. Some regions were slightly denser than others, and gravity began to pull matter together. Dense regions became denser. They attracted more matter. Over millions of years, these clouds collapsed, heating up as they compressed. Eventually, in the densest regions, the temperature and pressure became high enough for nuclear fusion to begin. The first stars ignited. These first stars were massive, hundreds of times more massive than our Sun. They were short-lived, burning through their fuel in just a few million years before exploding as supernovas. But those explosions were critical. They created heavy elements: carbon, oxygen, nitrogen, iron. All the elements heavier than helium are created inside stars or in supernova explosions. Those elements were scattered into space, mixing with the hydrogen and helium clouds. New stars formed from that enriched material. Some of those stars had planets, and those planets, for the first time, contained the elements necessary for life. This process repeated over billions of years. Stars formed, lived, died, and scattered heavy elements into space. Each generation of stars was slightly richer in heavy elements than the last. Our Sun is a third-generation star, maybe even fourth generation. It formed about 4.6 billion years ago from a cloud of gas and dust that had been enriched by previous generations of stars. That cloud collapsed under its own gravity, most of the mass concentrating in the centre to form the Sun. But not all of it. Some of the material remained in a disk orbiting the young Sun, and in that disk particles collided and stuck together. Dust grains became pebbles, pebbles became rocks, rocks became boulders, boulders became planetesimals, and planetesimals collided and merged to form planets. Earth formed this way. It started as a ball of molten rock, bombarded constantly by debris left over from the solar system's formation. The early Earth had no atmosphere, no oceans, no life. It was a hellish place, with surface temperatures hot enough to melt rock. But over time, it cooled. Water vapor in the atmosphere condensed and fell as rain. Oceans formed. The bombardment slowed as the solar system cleared out most of the remaining debris. Earth became more stable, more hospitable, and then somehow life began. We don't know exactly how. This is one of the great unsolved questions in science. We know that life on Earth started relatively quickly, geologically speaking. The oldest evidence of life dates back to about 3.8 billion years ago, less than a billion years after Earth formed. That's fast. It suggests that given the right conditions, life might arise readily. But we don't know what those conditions are or what sequence of chemical reactions led from non-living matter to living cells. What we do know is that once life started, it persisted, it evolved, it diversified. For billions of years, life on Earth consisted entirely of single-celled organisms, bacteria and archaea, simple cells without nuclei, living in the oceans, in the soil, in extreme environments. They transformed the planet. Some of them developed the ability to photosynthesize, using sunlight to convert carbon dioxide and water into sugar and oxygen. This was revolutionary. Oxygen built up in the atmosphere over hundreds of millions of years, changing Earth's chemistry and creating the conditions for more complex life. About 2 billion years ago, a critical event occurred. One cell engulfed another, and instead of digesting it, the two formed a symbiotic relationship. The engulfed cell became a mitochondrion, the powerhouse of the cell, producing energy. This was the origin of eukaryotic cells, complex cells with nuclei and internal structures. All complex life on Earth, all plants, animals, fungi, all of it descended from this event. For another billion years, life remained mostly single-celled. But then, about 600 million years ago, something changed. Multicellular life exploded in diversity. The Ediacaran period saw strange, soft-bodied organisms unlike anything alive today. The Cambrian explosion followed, a period of rapid diversification, where most of the major animal groups that exist today first appeared in the fossil record. Fish evolved, then amphibians, then reptiles. Dinosaurs ruled the Earth for over 160 million years, before an asteroid impact 66 million years ago wiped them out, along with about 75% of all species on Earth. But that catastrophe created an opportunity. With the dinosaurs gone, mammals diversified, primates evolved. About 6 million years ago, our lineage split from the lineage that led to modern chimpanzees. Over millions of years, our ancestors evolved larger brains, developed the ability to walk upright, created tools, mastered fire. About 300,000 years ago, anatomically modern humans appeared. And about 70,000 years ago, something extraordinary happened. Humans developed complex language, symbolic thinking, culture. We began to create art, tell stories, pass knowledge from generation to generation. That's what had to happen for you to exist. The universe had to begin. Stars had to form and die, creating heavy elements. Our sun and solar system had to form from the debris of those dead stars. Earth had to cool and develop oceans. Life had to begin and survive for billions of years. Evolution had to produce increasingly complex organisms. Extinction events had to occur at just the right times to clear the way for new forms of life. Your ancestors had to survive predators, diseases, famines, wars, an unbroken chain of survival stretching back billions of years, every single one of your ancestors successfully reproducing before they died, all so that you could exist right now. The odds are astronomical. If any single event in that chain had gone differently, you wouldn't be here. A different sperm cell fertilizes the egg, and you don't exist. Your parents never meet, and you don't exist. The asteroid that killed the dinosaurs misses Earth, and mammals never diversify, and humans never evolve, and you don't exist. The universe is slightly different in the moments after the Big Bang, and galaxies don't form, and stars don't form, and you don't exist. You are the result of an almost infinite series of improbable events. You are the universe made conscious, a collection of atoms that came from exploded stars, arranged in such a way that they can think and feel and wonder about their own existence. That's not just extraordinary, it's miraculous in a secular sense. Not miraculous as in supernatural, but miraculous as in so unlikely that it borders on impossible. And yet here you are. The atoms in your body are ancient. The hydrogen in your body, the hydrogen in the water you drink, in the air you breathe, most of that hydrogen has existed since the Big Bang. It's 13.8 billion years old. The carbon, the calcium, the iron in your blood, those atoms were forged in the cores of stars that died before our sun was born. You are literally made of stardust. That's not poetic exaggeration. That's literal fact. The matter that makes up your body was created in stellar furnaces billions of years ago. You are the universe experiencing itself. Every thought you have, every emotion you feel, every moment of wonder or sadness or joy, that's the cosmos becoming aware of its own existence. Through you, the universe knows what it's like to be alive, to be conscious, to look up at the night sky and feel awe. And you're not alone in this. Every person on Earth shares this story. Every human being is made of the same stardust, shaped by the same evolutionary processes, descended from the same single-celled ancestors that arose in Earth's ancient oceans. We are, all of us, family in the deepest possible sense. Not just humans, but all life on Earth. The trees outside your window, the birds in the sky, the bacteria in your gut, all of it related, all of it part of one vast interconnected web of life that has persisted for billions of years. This perspective should change how we see each other. The conflicts between nations, the divisions based on race or religion or ideology, all of it seems absurd when you remember that we're all made of the same stuff, all products of the same cosmic and biological history. We're fighting over a tiny planet in an incomprehensibly vast universe. dividing ourselves based on arbitrary distinctions when we're all fundamentally the same. We're all conscious matter, briefly aware, trying to make sense of our existence before we return to unconsciousness. Let's think about what happens next, both in the near future and the distant future. In the near future, humanity faces enormous challenges: climate change, resource depletion, political instability, the risk of nuclear war, pandemics, the development of artificial intelligence that might surpass human intelligence. These are real threats. They could end our civilization or even our species, but they're also challenges we can potentially overcome if we choose to. We have the knowledge, the technology, the resources. What we need is the will, the cooperation, the long-term thinking to address these problems before they become catastrophic. If we survive the next few centuries, if we navigate these challenges successfully, what could we become? Humanity's potential is enormous. We're already beginning to explore space. We've sent robots to other planets. We've landed humans on the moon. It's been over 50 years since the Apollo missions, and we haven't gone back yet, but that will change. Plans are in development to return to the moon, to establish a permanent presence there, to eventually send humans to Mars. Mars is a difficult target. It's cold, dry, bombarded by radiation. It has no magnetic field to protect against solar wind. Its atmosphere is too thin to breathe and too thin to provide much protection from meteorites. But it's also the most Earth-like planet in the solar system. It has water ice at the poles, and beneath the surface, it has a day that's roughly 24 hours long. It has seasons. With enough technology and effort, we could potentially terraform Mars over thousands of years, giving it a thicker atmosphere, warming it up, making it more habitable. Or we could live in domed cities or underground habitats, creating artificial environments that sustain human life. It would be hard, it would take generations, but it's possible. And if we do it, if we establish a self-sustaining human presence on another planet, that changes everything. It means humanity is no longer confined to Earth. It means we have a backup, a second chance if something catastrophic happens to our home world. Beyond Mars, there are the moons of the outer solar system. Europa, orbiting Jupiter, has a global ocean beneath its icy crust. That ocean might contain life, simple microbial life adapted to the dark, cold, high-pressure environment. Enceladus, a moon of Saturn, also has an underground ocean, and we've detected organic molecules in the plumes of water vapor it ejects into space. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface and a thick atmosphere. It's a bizarre world, cold and alien, but it has weather, seasons, an active hydrological cycle. These places are potential targets for human exploration, maybe even colonization, though the challenges are immense. Jupiter and Saturn are far from the Sun. Their moons receive very little sunlight. Temperatures are hundreds of degrees below zero. The radiation environment around Jupiter is deadly. Any humans visiting Europa would need heavy shielding just to survive. But none of these challenges are insurmountable in principle. They're engineering problems. Difficult engineering problems, yes, but problems that might be solvable with advanced enough technology. Looking even farther ahead, we can imagine humanity spreading beyond the solar system, building generation ships or developing faster propulsion systems, sending colonists to other star systems, to planets orbiting other suns. This would be a multi-generational project. The nearest star is over 4 light-years away. Even travelling at a significant fraction of the speed of light, it would take decades to reach. And we're nowhere close to building engines that can propel spacecraft to those speeds. But maybe someday, maybe in 1,000 years, maybe in 10,000, humanity will have spread across the galaxy. We might terraform planets, build habitats in space, adapt ourselves genetically or technologically to survive in extreme environments. We might encounter other civilizations, other forms of intelligent life that evolved independently on other worlds. Or we might not. We might be alone, the only intelligence in the galaxy, perhaps in the entire observable universe. If we are alone, that places an extraordinary responsibility on us. We are the universe's only way of knowing itself, at least in this region of space. If we fail, if we destroy ourselves, we silence that awareness. The universe continues, vast and uncaring, but unconscious once again. No one left to observe the stars, to ask questions, to seek understanding. That would be a tragedy of cosmic proportions. But if we're not alone, if there are others out there, then our future might involve contact, communication, perhaps even cooperation with alien civilizations. What would that be like? We can't know. We can't predict what an alien intelligence would value, how it would think, whether it would be friendly or hostile or indifferent. But it's one of the most profound questions we can ask. Are we alone? And if not, what happens when we meet them? These are questions we might answer in the coming centuries, or we might never answer them. The universe might be too large, the distance is too vast, for civilizations to ever make contact. We might be surrounded by other intelligent species, all of us isolated by the tyranny of distance, all of us looking up at our respective skies and wondering if anyone else is out there, none of us ever receiving an answer. But let's return to the present one more time. Let's return to Earth, to you, to the here and now. You've journeyed across the observable universe. You've confronted scales that are incomprehensible. You've seen how small Earth is, how tiny and insignificant it appears when compared to galaxies and superclusters and the vast cosmic web. And yet, Earth is home. It's the only home humanity has ever known. Every generation of humans that has ever lived was born on Earth, lived on Earth, died on Earth. Every story, every achievement, every moment of beauty or tragedy, all of it happened here. Earth might be a pale blue dot, a tiny speck in a vast cosmos, but it's our pale blue dot, and it deserves our care, our protection, our respect. We're living through a critical moment in human history. For the first time, we have the power to significantly alter Earth's climate, to drive species to extinction at rates not seen since the asteroid impact that killed the dinosaurs, to deplete resources faster than they can regenerate. We're also, for the first time, beginning to understand our place in the cosmos. We know Earth is small, we know the universe is vast, we know we're not the centre of anything. We're just one planet among trillions, orbiting an average star in an average galaxy. That knowledge should humble us. It should make us think carefully about how we use our power, how we treat our planet, how we treat each other. Because right now, Earth is all we have. We're not colonizing Mars anytime soon. We're not escaping to other star systems. For the foreseeable future, for the next several generations at least, humanity's fate is tied to Earth's fate. If we destroy Earth's biosphere, we destroy ourselves. There's nowhere else to go. The universe might be vast, but the habitable parts of it are vanishingly rare. And Earth, as far as we know, is the only place in the entire cosmos where life exists. That makes it precious beyond measure. Every forest, every ocean, every species, they're all irreplaceable. If we lose them, they're gone forever, and we're losing them. Species are going extinct at an alarming rate. Forests are being cut down. Oceans are warming and acidifying. The climate is changing faster than at any point in human history. These are solvable problems. We have the knowledge and the technology to address them. What we lack is the collective will, the long-term thinking, the ability to prioritize the future over short-term gains. But maybe, just maybe, understanding our place in the cosmos can help with that. Maybe if enough people truly grasp how small Earth is and how vast everything else is, they'll start to see our planet differently. not as an infinite resource to be exploited, but as a fragile oasis in a vast desert, the only place in the observable universe where we know for certain that life exists. The scale of the universe should inspire awe, but it should also inspire responsibility. We are, as far as we know, the universe's only conscious observers in this region of space. Through us, the cosmos knows itself. That's not a small thing, that's enormous. And it comes with obligations. We have an obligation to preserve Earth's biosphere. We have an obligation to seek knowledge, to explore, to ask questions. We have an obligation to survive, to persist, to ensure that this brief moment of cosmic awareness doesn't end prematurely. We have an obligation to each other to recognize our shared humanity, to work together despite our differences. Because in the grand scheme of things, our differences are tiny. We're all humans, all made of the same stardust, all living on the same small planet. The things that divide us, nationality, religion, race, ideology, they're all human constructs. They're important to us, yes, but they're not fundamental. What's fundamental is that we're alive, we're conscious, and we're together on this small world. Everything else is details. Let's think about legacy for a moment. What will humanity leave behind? If we survive for millions of years, if we spread across the galaxy, what mark will we make on the universe? Or if we don't survive, if we're just a brief flicker of consciousness that arises and fades within a few thousand years, what will remain of us? The answer, in cosmic terms, is probably nothing. The structures we build, even our most impressive monuments, will erode and crumble. The pyramids of Egypt have stood for thousands of years, but give them a few 100 million years and they'll be dust, worn away by wind and water and geological processes. The faces on Mount Rushmore will eventually erode into unrecognizable shapes. The satellites we've sent into orbit will fall back to Earth or drift into the sun. Even our radio signals, the first of which left Earth less than a century ago, will weaken and scatter as they spread through space. They're travelling outward in an expanding sphere, but the signal strength decreases with distance. Eventually they'll be too weak to distinguish from background noise. If aliens with powerful enough receivers happen to be within that expanding sphere, they might detect our signals. They might learn that we existed. But the sphere is only about 100 light-years in radius right now. That's a tiny fraction of the galaxy. Most of the Milky Way hasn't been reached by our signals yet, and if we stopped broadcasting tomorrow, the sphere would just keep expanding at the speed of light, carrying our old radio and television programs into the void, growing weaker and weaker until eventually they fade completely. So our physical legacy might be nothing. In a billion years, there might be no evidence that we ever existed. Earth will still be here, probably, though it will be much hotter because the sun gradually gets brighter as it ages. But any traces of human civilization will be long gone, buried under layers of rock and sediment, worn away by erosion, consumed by geological processes. But maybe our legacy doesn't have to be physical. Maybe our legacy is knowledge, understanding, the accumulated wisdom of a species that learned to think, to question, to explore. We've figured out the laws of physics that govern the universe. We've mapped the human genome. We've sent spacecraft to other planets. We've looked back in time to the cosmic microwave background, seeing the universe as it was less than 400,000 years after the Big Bang. We've detected gravitational waves from colliding black holes billions of light-years away. We've taken pictures of the event horizon of a supermassive black hole. These are incredible achievements. They represent thousands of years of cumulative human effort, generations of scientists and thinkers building on each other's work, slowly piecing together an understanding of reality. And that knowledge is fragile. It exists in books, in databases, in the minds of living humans. If civilization collapses, if we lose the ability to maintain our technology, that knowledge could be lost. It's happened before on smaller scales. The Library of Alexandria burned. The knowledge of how to make Roman concrete was lost for over 1,000 years. Entire civilizations have risen and fallen, and much of what they knew disappeared with them. We like to think we're different now, that we have redundant systems, that information is backed up and distributed, and to some extent that's true, but it's also true that much of our knowledge depends on complex technological systems. If those systems fail, if we can't maintain them, we might lose access to vast amounts of information even if the data physically still exists. How many people today could build a computer from scratch starting with raw materials? How many people could perform surgery without modern tools and antibiotics? How many could navigate by the stars? We've become incredibly specialized. We rely on each other, on the vast interconnected web of modern civilization, to maintain our standard of living and our knowledge base. That's a strength in some ways. Specialization allows for incredible depth of knowledge. But it's also a vulnerability. If something disrupts that web, we might not be able to maintain what we've built. This is why preserving knowledge is so important, why education matters, why we need to keep asking questions, keep exploring, keep pushing the boundaries of what we know. Because knowledge is humanity's real treasure. It's what separates us from other animals. It's what allows each generation to build on the accomplishments of the previous one rather than starting from scratch. And it's what might allow us to survive long term, to navigate the challenges we face, to avoid the pitfalls that could end our civilization. The universe is indifferent to whether we survive or not. It doesn't care. Stars will keep burning, galaxies will keep spinning, the cosmic expansion will continue. None of it depends on us. But we care. We have to care. Because we're the ones living this existence. We're the ones who get to experience the universe. And that experience is worth preserving. Life is rare. Consciousness is precious. The fact that matter organized itself into patterns complex enough to think and feel and wonder, that's not something to take for granted. It's something to celebrate, to protect, to nurture. Think about your own life for a moment. Your experiences, your memories, your relationships, your hopes for the future. All of that exists because of an almost infinitely improbable chain of events stretching back to the beginning of time. And all of it will end. You will die someday. That's not morbid. It's just fact. Every human who has ever lived has died or will die. Death is part of life. It's what gives life meaning, in a way. If you had infinite time, nothing would be urgent. Nothing would be precious. But you don't have infinite time. You have decades, if you're lucky. Maybe 80 or 90 years, maybe less. And in that finite time, you get to experience being alive. You get to see sunsets, taste food, listen to music, feel the warmth of another person's hand in yours. You get to learn, to grow, to change. You get to make choices about how you spend your limited time. And those choices matter. Not in a cosmic sense, maybe. The universe doesn't care whether you're kind to others or selfish, whether you pursue your dreams or settle for less, whether you leave the world a little better than you found it or a little worse. But you care, and the people around you care, and that's enough. Your life is small in cosmic terms. You're one person among 8 billion, living on a planet that's a speck of dust in an incomprehensibly vast universe. But your life is everything to you. It's your entire existence, and it's precious. The fact that you get to exist at all, that you get to be a conscious observer of reality for a brief moment in cosmic time, that's extraordinary. Don't waste it. Don't spend your life doing things that don't matter to you. Pleasing people whose opinions you don't value, pursuing goals that someone else set for you. You have limited time. Use it wisely. Do things that bring you joy, that bring others joy. that make the world a slightly better place. Connect with other people, learn new things, experience as much as you can, leave a positive mark, even if it's small, even if it's just in the lives of a few people who will remember you fondly when you're gone. That's a good life. That's a life worth living. And in a universe that's vast and cold and indifferent, choosing to live well, to be kind, to seek knowledge and beauty and connection, that's an act of defiance. It's saying that even though we're small, even though we're temporary, what we do still matters to us. Let's zoom out one more time and think about the ultimate questions. Why does the universe exist? Why is there something rather than nothing? These are questions that science can't currently answer. Science is incredibly good at explaining how things work. It can tell you how stars form, how life evolves, how galaxies cluster. But it can't tell you why any of it exists in the first place. Why are there laws of physics? Why do those laws take the specific form they do? Why is there a universe at all? Some people find answers to these questions in religion, in the idea of a creator, a god or gods who brought the universe into being for some purpose. Others are comfortable with the idea that there might not be a why, that the universe simply exists as a brute fact, without reason or purpose, and that any meaning we find in it is meaning we create ourselves. Science doesn't have much to say about this. It's outside the scope of what science investigates. Science deals with testable hypotheses, with observations and experiments. You can't test the hypothesis that God created the universe. You can't run an experiment to determine if there's ultimate meaning to existence. These are philosophical and theological questions, not scientific ones. But here's what we do know. The universe exists. You exist. And for as long as you exist, you get to be part of this vast cosmic story. You're made of atoms that were forged in the cores of ancient stars. You're the product of billions of years of evolution. You're a conscious mind, capable of understanding your own existence and contemplating the nature of reality. That's remarkable. Whether the universe was created with purpose or arose by chance, whether there's ultimate meaning or meaning is something we construct, none of that changes the fact of your existence right now. You're here, you're alive, you're aware, and you get to decide what to do with that. Some people find that terrifying, the idea that there might not be cosmic purpose, that we might be accidents, brief sparks of consciousness in an indifferent universe that can feel isolating, meaningless. But it can also be liberating. If there's no predetermined purpose, then you're free to create your own. You get to decide what matters to you. You get to choose your own values, set your own goals, define your own version of a meaningful life, and you're not alone in that. You're surrounded by other humans, all of them grappling with the same questions, all of them trying to find meaning and purpose in a vast, confusing universe. We're in this together. All 8 billion of us living on this small planet trying to make sense of existence. We have different answers, different philosophies, different religions, different worldviews, and that's okay. That's part of what makes humanity interesting. We don't all have to agree on the big questions. We just have to agree to coexist, to respect each other's search for meaning, to work together on the practical challenges we face. Because regardless of what we believe about ultimate meaning, we all share this planet. We all need clean air and water. We all benefit from peace and stability. We all lose if civilization collapses or if we destroy Earth's biosphere. Those are common interests that transcend our philosophical differences. Let's think about the far future again. Not hundreds or thousands of years, but millions and billions of years. What could become of consciousness in the universe? If humanity survives and spreads, we might transform ourselves in ways we can barely imagine. We might merge with our technology, becoming post-human entities with capabilities far beyond current human limitations. We might upload our minds into computers, living in virtual realities of our own design. We might genetically engineer ourselves, adapting to life in space or on other planets, branching into multiple species, each suited to different environments. Or we might stay fundamentally human, preserving what we are even as we spread across the galaxy. We might seed other planets with Earth life, creating new biospheres, new Earths scattered among the stars. We might encounter other civilizations and learn from them, sharing knowledge, perhaps even sharing genetic or cultural material, creating hybrid civilizations that combine the best of multiple worlds. Or we might be alone. We might spread across the entire galaxy and never find anyone else. The galaxy might be ours for the taking, empty of other intelligent life, waiting for us to fill it. If that's the case, then what we do matters even more. We're not just preserving human civilization, we're preserving the possibility of consciousness itself in this galaxy. If we fail, the Milky Way might remain dark, lifeless, silent for billions of years. Eventually other civilizations might arise. Evolution might produce intelligence again on some distant world. But that could take billions of years, and there's no guarantee it will happen. We might be the galaxy's only chance at consciousness for a very long time. That's a heavy responsibility. But it's also an incredible opportunity. We could be the ancestors of a galactic civilization, the original humans from which trillions of descendants spread across hundreds of thousands of worlds. Our descendants might be so different from us that we wouldn't recognize them as human, but they would trace their lineage back to us, to Earth, to this moment in history when humanity was young and just beginning to understand its place in the cosmos. Imagine that future. Billions of years from now, long after the sun has died, long after Earth itself has been destroyed, there might still be beings who remember where they came from. They might preserve records of Earth, of the species that evolved here, of the first tentative steps into space. They might visit the ruins of our solar system, now cold and dark, and pay their respects to the world that gave birth to their ancestors. Or maybe they won't. Maybe by then we'll have been forgotten. Maybe the lineage will have diverged so much that the connection to Earth is meaningless. Maybe our descendants will be so different, so transformed by millions of years of evolution and technological change, that the idea of humanity as we understand it will seem quaint, primitive, barely worth remembering. Either way, the future is vast, the possibilities are endless, and it starts here, now, with us, with the choices we make in the next few decades and centuries. Do we destroy ourselves? Do we stagnate and decline? Or do we grow, adapt, spread, and become something greater than we are now? The answer depends on us, on whether we can overcome our divisions, our short-term thinking, our self-destructive tendencies, on whether we can learn to think on cosmic timescales, to value the future as much as the present, to see ourselves not just as individuals or nations, but as a species, a family, a single entity with a shared fate. It's not easy. Humans evolve to think in terms of immediate threats and rewards. We're good at responding to things we can see and touch, to dangers that are right in front of us. We're not good at responding to abstract long-term threats like climate change or resource depletion. Our brains didn't evolve for that. But we have something other animals don't. We have the ability to override our instincts with reason. We can think abstractly. We can plan for the future. We can choose to act against our immediate interests for the sake of long-term survival. We've done it before on smaller scales. We've built civilizations, created laws, established systems of cooperation that allow millions of people to live together in relative peace. We can do it again on a larger scale. We can choose to think globally, to cooperate internationally, to make the sacrifices necessary to ensure a future for our species and our planet. But we have to choose it. It won't happen automatically. The default trajectory, if we don't actively work to change it, might be collapse. Civilizations have collapsed before. Entire societies have disappeared, leaving behind only ruins. We could be next, or we could be the generation that breaks the pattern, that learns from history, that builds something lasting. Let's return to the scale of the universe one more time, because it's easy to get lost in these grand visions of the future and forget just how small we are right now. Earth is tiny. Our entire civilization, everything we've built, every achievement we're proud of, all of it exists on a planet that's barely visible from the edge of our own solar system. From the nearest star, you couldn't see Earth at all, even with the most powerful telescope. It would be lost in the glare of the sun. From another galaxy, our entire solar system would be invisible. The sun would be just one star among hundreds of billions, indistinguishable from countless others. And from the edge of the observable universe, the Milky Way itself is just a faint smudge of light, one galaxy among trillions. At that scale, Earth doesn't just disappear, it becomes so insignificant that it's hard to comprehend. If you made a scale model of the observable universe where the Milky Way was the size of a coin, Earth would be far smaller than an atom. It would be smaller than a quark. It would be so incomprehensibly tiny that there's no physical object you could compare it to. It would be, for all practical purposes, nothing. And yet, on that nothing, life exists. Consciousness exists. You exist. The universe is vast and mostly empty, mostly dead. But here, on this tiny world, matter has organized itself into living things, into thinking things, into beings capable of understanding the universe itself. That's extraordinary. That's the miracle, if we can use that word. Not a supernatural miracle, but a natural one. The miracle of complexity arising from simplicity, of consciousness emerging from unconscious matter, of the universe waking up and looking at itself through your eyes. When you look up at the night sky, you're not separate from the universe. You are the universe. You're a small part of it, yes, but you're a part nonetheless. The atoms in your body, the neurons firing in your brain, the thoughts you're having right now, all of that is the universe doing something it does in very few places. It's becoming aware, it's thinking, it's wondering about its own existence. And that's beautiful. It's tragic too, because it's temporary. Your awareness will end when you die. And someday, perhaps trillions of years from now, all consciousness in the universe might end. The stars will burn out, the universe will grow cold and dark, and there will be no one left to observe it, no one left to care. But that's trillions of years away. For now, the universe is young. It's full of stars and galaxies and planets, and on at least one of those planets, life. And that life has produced you. You get to experience this. You get to be conscious, to think, to feel, to wonder. You get to look up at the stars and know what they are, to understand your place in the cosmos, to grapple with questions that might not have answers. That's your gift. That's what being human means. It means being small and temporary and fragile, but also being aware, being curious, being capable of understanding things far larger than yourself. Don't take that for granted. Don't waste your time on Earth consumed by trivial concerns, by anger and fear and pettiness. Yes, you have to deal with the practical realities of life. You have to work, to pay bills, to handle responsibilities. But don't let those things consume you entirely. Remember to look up occasionally. Remember to feel awe. Remember that you're part of something vast and ancient and ongoing. Remember that you're made of stardust, that you're a temporary arrangement of atoms that was forged in stellar furnaces billions of years ago and will eventually return to the universe in some other form. Let's think about what happens when you die. Your consciousness ends. Your subjective experience of being you stops. But the atoms that make up your body don't disappear. They return to the Earth, to the biosphere. If you're buried, those atoms might be absorbed by plants, by bacteria, by fungi. They might become part of other living things. If you're cremated, they return to the atmosphere, to the soil. Either way, they persist. The carbon in your body might become part of a tree 100 years from now. The calcium in your bones might become part of a rock formation. The hydrogen might end up in a river, in the ocean, eventually in raindrops falling on some future landscape. You're not permanent, but you're not gone either. Not completely. You transform. You become part of the ongoing cycle of matter and energy that has been running since the Big Bang and will continue running long after human civilization has ended. That's a kind of immortality, perhaps. Not the immortality of consciousness, not the persistence of you as an individual, but the immortality of matter, of the fundamental stuff you're made of. That stuff is eternal, or as close to eternal as anything can be in a universe that had a beginning and might have an end. And if you have children, if you pass on your genes, then part of you persists in another way. Your descendants will carry pieces of your DNA, fragments of the genetic code that made you who you are. That code will mix with other codes, recombining, changing, evolving, but traces of you will persist through generations, perhaps for thousands or millions of years, until your lineage either dies out or becomes so diluted through mixing with other lineages that it's no longer meaningful to say that any particular individual is descended from you. But even then, even if your specific genetic lineage ends, you're part of the human family tree. You're connected to every other human through common ancestors. Go back far enough, and we're all cousins. Go back farther, and we're all related to every other living thing on Earth. We share common ancestors with trees, with fish, with bacteria. All life on Earth is one family, one vast interconnected web stretching back billions of years to the first cells that learned to reproduce themselves. You're part of that. Your existence is proof that the chain hasn't broken, that life has persisted through mass extinctions, through ice ages, through asteroid impacts and volcanic eruptions and every other catastrophe Earth has experienced. Your ancestors survived all of that, and you carry their legacy forward. Now, let's bring this full circle. We started with you, sitting wherever you are, occupying a small space, living your life. And we zoomed out, farther and farther, until Earth disappeared. Until the solar system disappeared, until even galaxies became specks in the vastness of the observable universe. And along the way, something changed in your perspective. You felt it, that sense of being small, of being insignificant in cosmic terms, but also that sense of being connected, of being part of something vast and ancient and ongoing. Both of those feelings are true. You are small. In cosmic terms, you barely exist. Your life is a brief flicker, a moment of consciousness in a universe that's been around for 13.8 billion years and will persist for trillions more. But you're also significant. You're a part of the universe that's become aware of itself. You're matter that can think and feel and wonder. And that's rare. As far as we know, it might be common. The universe might be full of conscious beings, scattered across trillions of planets, all looking up at their own skies and wondering if they're alone. Or it might be rare. Earth might be one of very few places where life arose, where evolution produced intelligence, where consciousness emerged. We don't know, but either way you matter. Your existence matters. Not because the universe cares. The universe doesn't care. It's not capable of caring. But you care, and that's enough. You have this one life, this brief moment of awareness. What you do with it is up to you. You can spend it in pursuit of happiness, of knowledge, of connection with others. You can try to leave the world a little better than you found it. You can create, learn, explore, love. or you can waste it, let it slip away in distraction and regret. The choice is yours, and it's a choice you make every day with every action, every decision, every moment of your attention. The universe is vast, Earth is tiny, you are small, but you're also here, now, alive, aware, and that's extraordinary. Don't forget that. When you're caught up in the stress and hassle of daily life, when you're worried about money or work or relationships or health, remember to step back occasionally. Remember the bigger picture. Remember that you're standing on a planet that's hurtling through space at thousands of miles per hour, orbiting a star that's one of hundreds of billions in a galaxy, that's one of trillions in an observable universe that might be just a tiny fraction of total reality. Remember that you're made of atoms that are billions of years old, that you're the product of an unbroken chain of life stretching back to the first cells in Earth's ancient oceans. Remember that you're conscious, that you can think and feel and wonder, that you're the universe experiencing itself. And then, with that perspective, with that sense of awe and humility and connection, go live your life. Be kind to others. They're in the same situation you are, small and temporary, trying to make sense of existence. Be curious. Keep learning. The universe is full of mysteries, and every answer leads to new questions. Be grateful. You didn't have to exist. The odds against your existence were astronomical. But here you are anyway, given this brief opportunity to experience being alive. Make the most of it. And remember always that Earth is tiny, but it's home. It's the only home we have. The only place in the vast cosmos where we know for certain that life exists. Treat it well. Protect it. Because in the end, we're all in this together, all 8 billion of us, sharing this small world, looking up at the same stars, wondering about the same mysteries, trying to understand our place in the universe. Thank you for joining me on this journey tonight. Thank you for taking the time to contemplate the true scale of the universe and your place within it. If this exploration has changed your perspective even a little, if it's made you think about things differently, then it's been worthwhile. If you found this meaningful, please consider liking this video and subscribing to the channel. It helps more people discover these journeys into the cosmos. And remember, you're standing on a planet that's incomprehensibly small when compared to the universe. But you're also standing on the only world we know that's home to life, to consciousness, to wonder. That's something to celebrate, that's something to protect. Sleep well tonight, knowing that you're part of something vast and beautiful and mysterious. The universe is enormous beyond comprehension. Earth is tiny beyond measure, but Earth is precious, and you, living on this small world, are part of its story. Good night.